morning. We start with the fourth lecture on the subject on physical metallurgy, and we continue with the first chapter, that is on atomic bond and crystal structure. And the last class we talked about point lattice, which is used to represent crystal structure in a material. We looked at atomic arrangement in a few simple crystal structures that we find in metal, namely face centered cubic, body centered cubic and hexagonal closed pack structure. We also looked at the packing density, the relationship between the atomic diameter and the lattice parameter, and also introduced the concept of Miller indices to represent planes and directions in a crystal. In the end, we talked about stereographic projection, which is an angle to projection, and this is very frequently used to solve problems in crystallography. Now, today we shall look at particularly stereographic projection in great detail. And to recapitulate, look at this octahedral site we talked about in the last class. This is a body centered cubic structure. The main atoms, they are located at the corner of the cube, and the interstitial sites are the edge center and face centered. We calculated the number of interstitial site in a unit cell, and here you will clearly see that number of interstitial sites. How to calculate, that is given here. Each of these edge center is shared by 4 unit cell, which are placed around this edge. So, therefore, contribution of edge center atom will be 12 times 1/4, and then we also have face centered, and this is shared by 2 neighboring unit cell. The contribution of each towards the unit cell is half. So, therefore, if you add these up, it comes out to be 6. So, that means there are 6 interstitial sites of octahedral type in a unit cell, and this incidentally happens to be 3 times the number of atoms in a BCC lattice. Similarly, we looked at tetrahedral sites. Tetrahedral sites are made up of 4 triangular faces. Now, each of these triangle is an isosceles triangle. 2 edges are equal to half the diagonal, say like this and this, and the other edge is equal to the edge of the cube, that is lattice parameter A. So, this is A, this will be √3 A over 2. So, and here also you can calculate the number of interstitial site, which is given here. Here all the 4 sites in a face, they will belong to 2 unit cell, one this, one on top of this. So, and there are 6 faces. So, total number of sites is 4 times 6, that is 24, and each face being shared by 2 unit cell, the net contribution comes out to be 4 into 6 times half. So, this comes out to be 12. So, therefore, it is 6 times the number of atom in a unit cell. And last time we also calculated the packing density. So, this packing density, it is the gaps are divided into octahedral and tetrahedral sites. So, here you have more number of sites. So, obviously, this is going to be smaller than octahedral sites. And here is a method which is illustrated in to calculate the gap or dimension of the interstitial site. Octahedral sites is much easier to visualize. These are the 4 corner atom on the face, and this is the phase center, which is an octahedral site in a BCC structure, and you have 8 equilateral 8 isosceles triangles basically. So, this is dimension A, and this dimension is half of the diagonal. So, you have 8 faces surrounding this interstitial site, and the atomic diameter we estimated last time, this is equal to root 3 a by 2. So, once you know this, then it is possible to calculate this gap. Now, this distance between this atom and this atom is equal to a, and therefore, the gap along c axis will be this distance a minus this atomic diameter, because half of this atom and half of this atom add together to one atom. So, one atomic diameter you subtract, you get the gap along c axis. But in this if you calculate the gap along the diagonal, in the same way the diagonal is, this is a, this is a. So, the diagonal is a root 2. So, if the gap in the face diagonal therefore, will be a times root 2 minus 3 by root 3 by 2, and obviously, this is larger than this. So, therefore, what it says that this site is asymmetric. If you try to put an atom, it will get these two will get displaced more than these two. In the same way, it is possible to calculate the interstitial site's dimension in case of tetrahedral site, which is shown here. It is possible to find out the coordinates of each of the corner atoms. Basically, you have one corner atom here, one corner atom, and this distance is a. Similarly, you have one face center atom, another face center atom. So, this coordinate, if you say 0 0 0, this coordinate is half half half, and these diagonal, this is half the face diagonal, which is equal to a root 3 over 2. So, therefore, the distance between any of these any of these corner point with this interstitial site, it is possible to find out from geometrical relationship. Say if, so this is the coordinate, half 1/4 0 is the coordinate of this site, and if you try to find out distance between this coordinate and this, it will clearly come out to be a root 5 over 4. We also looked at Miller indices of for crystal plane. Say these are the crystal axis A, B, C, and if you represent an atom in terms of this fractional indices or intercepts, like this is a plane which intercepts A axis at 1 over h, B axis 1 over k, C axis at 1 over L, then the indices of this plane we call it, we define it as HKL, which is the reciprocal of these intercepts. And we represent this particular plane as HKL, but in the crystal, because of symmetry, there will be several planes which may be similar, having HKL indices. The atomic arrangement of similar, and this set of such planes are represented by this curl bracket. In the same way, it is possible to represent the directions, particularly this is a crystallographic direction, which we represent simply by these coordinates in terms of this crystallographic axis. So, you move, if this coordinate is u v w, that means you move u distance along a axis, v distance along b axis, and w distance along c axis. And here also similar directions, if you want to represent, we represent it in terms of this angular brackets. And always in a crystallography type of system that you use, all similar planes have similar indices. Now, in case of a hexagonal crystal, these are the crystal axis H, K, L, and here also you can apply the same concept, but here last time it was shown that say this particular plane, this is a prism plane. Now, this prism plane, its indices is 1 0 0 Miller indices, whereas if we take this particular plane, this is also exactly similar plane, this also should have same indices, and this in fact it is a 0 1 0. But if you look at this particular plane, say this particular plane which intersects h at 1, k at -1. So, this is actually 1 -1 0. So, this and this, although they are same, indices are different. That is why in this case we make a there is a slight difference. We see that we use 4 indices. This is called Miller-Bravais indices H, K, I, L. I is actually redundant, and that this I is equal to minus H plus K, and a system of plane are represented like this. Same thing you can extend it to direction as well. Now, here it is little tricky. So, which is shown over here, because all these directions, say suppose if you want followed that earlier convention, then this direction should have been 1 1 0, but crystallographically this direction and this direction they are same. So, here also we use a 4 indices system U, V, T, W. The T is as such redundant, this is equal to minus 1/3 of U plus V. This capital U, V, W is the normal Miller indices, and smaller U, V, W is the Miller-Bravais system. So, with this set of conversion, it is possible to show that all these equivalent directions will have identical or similar indices. And later on we will see that this type of representation allows us to do lot of matrix calculations or vector calculation, or this will help you to geometrically to represent crystal planes and directions in a projection. Now, then we looked at the concept of stereographic projection. Say normal engineering projection, the distance, the relationship between the distance are maintained. If you take a projection as an engineering projection of a 3D object, the distance between 2 points, even if it is scaled down, it maintains a definite relationship even on the projection. Whereas, in case of a stereographic projection, it is no longer a distance to projection, it is an angle to projection. And the concept of this projection is illustrated here. You imagine the crystal to be very small, and it is placed in a at the center of an hemisphere like this, and the size of the crystal is so small in comparison to the sphere, that is any plane that you draw here, even on the top surface or bottom surface, they all will coincide, they will pass through the center of the sphere, and this will intersect the reference sphere along these great circles. So, this is one plane, this is another vertical plane. So, we call, so therefore, the list of assumptions are here. The reference sphere dimension is very large, crystal is very small. So, that all plane pass through the origin. Now, what is a stereographic projection? We try to illustrate this here. Say suppose here we have placed this crystal. Now, imagine and here this is the reference sphere. Now, draw a plane and the crystal, extend it to meet the reference sphere. It meets the reference sphere along this great circle. So, radius of this circle and the radius of the reference sphere, they are same. Now, draw a perpendicular to this and extend it to meet the reference sphere. It meets at point P. Now, let us try to project this point P onto this projection plane. Projection plane is this circle is the projection plane by placing a light source here. Imagine that this pole is marked by a dark color, say black. This is a transparent sphere. This is a black dot over here, and put a flush bulb over here and try and find out the line joining this and this, where does it intersect the projection plane. This is the projection plane and this is the line joining this and this particular point, and this is where it intersects the projection plane. We call this the stereographic projection of point P. And this plane also intersects the projection plane at these 2 points, and later on we will see that trace of this line, this great circle, will also be projected on the projection plane as a great circle. Now, the problem comes that if we take a projection like this, we can project all the point in the part of the hemisphere which is away from the source of light. What happens to the points or to the poles which appear in the hemisphere which contains the light source? Suppose this example is taken here. How do you represent the point Q? What we do? We draw a line, join this point Q with the center, extend it to meet the other half of the reference sphere. So, this is the diametrically opposite point of this, and we say that this is small q, and project this onto the projection plane and represent it by an open circle, not a filled in circle. So, which signifies this is a point in this hemisphere. Now, we look at the same thing. So far I was trying to explain you with respect to the 3-dimensional object. Now, what happens if we do the same thing on a 2D or represent in a 2 dimension? This is the projection plane. Now, here this is the plane which was drawn, this is the perpendicular and this is the projection here. So, this is still now here also this is a 3-dimension representation. We convert it into 2 dimension, then it will look like this. This is point east, this is point west. So, this is getting projected as east and west, these are the 2 points. This point P, it comes here, that means this pole is represented by its projection in a 2D like this, and this great circle is represented here as a plane, and we will see later the distance, the angular, this is an angle through projection and P is normal to this plane. So, this angular relationship must be maintained. So, here we will see that the distance, angular distance between this and this great circle, this will be 90 degree. Now, let us see how do you represent angles between planes. This is illustrated here, and here also we use the reference sphere. So, that means, in this drawing I am trying to still represent it in terms of a 3D diagram. So, take this is a plane, draw a normal to the plane which intersects the reference sphere at this point. Draw another plane, this is the other plane. Draw the perpendicular to this plane passing through the origin. So, this is the other plane, and these two planes they intersect along this line. Which is shown here. Now, to measure this angle, how do you measure this angle? You have to visualize a plane passing through these two lines, which is shown here, and then on that plane therefore, you can put a protector and measure the angle. So, this is the basic principle of measuring angle in a on a 3-dimension reference sphere. Now, poles in a reference sphere Now, in this reference sphere, we draw certain reference lines or planes. So, now this particular plane, this is a great circles. We also use a set of small circles which are drawn like this. So, they are called latitudes, and these are great circles, and we can draw similar great circles at regular interval. These are all great circles. Now, we represent any angle or any angular position of any pole on this sphere in terms of these angular coordinates. Suppose we want to represent this point here, we will represent it by two angles. Say one angle, say joining this pole rather this perpendicular line, that angle it subtends with this reference line. So, this angle is phi, which is measured along this great circle. Another angle is theta. Say we take, say this is the line here, this great circle it meets here, and we say this angle is theta. So, by these two coordinates theta and phi, we represent a point on the globe. So, this is very much similar to geographical globe, where we have a set of lines, say longitudes, they are great circles, and the latitudes are the small circles. If we take a projection of that kind of a ruled globe, we get a net called Wolf net, and this helps us to measure angles on the stereographic projections. Now, here these great circles, they are the longitudes, and these are the projections of the small circles called latitudes. Now, in a Wolf net, these lines are drawn at a regular angular interval, and usually for most calculation we use Wolf net, where these lines are drawn at an interval of 2 degrees. Now, I will try to show you an illustration. Say suppose this is a 2D projection, stereographic projection. Now, here are two poles, two crystallographic directions. How do you measure this angle? Using Wolf net. Now, place it over the wolf net. Now, here to measure an angle, both these poles must lie on one plane, and here it is not, and here one plane in a wolf net is represented by this longitude. So, they are not lying on any longitude. So, therefore, you cannot, it is difficult to measure with this position. Now, what we do? We try and rotate this, and by rotating we try to bring it in such a position that these 2 points, they lie on one longitude as shown over here, and this longitude is graduated at regular interval. Look at the coordinates, that latitude over here, latitude over here, and read the difference. So, therefore, this angular graduation read along this longitude is the angle between the 2 poles. Now, we very often use standard projection of certain crystals. We will mostly concentrate on cubic crystal, and let us try and understand how do we construct standard projection of a cubic crystal. This is illustrated here. Imagine, say this is a reference sphere. Place a crystal at the center. The crystal is very small with respect to the reference sphere. These are the crystallographic axes, and we will try to construct 001 standard projections. Now, if you extend these cube planes, they will intersect this plane here, here, and the other one will intersect this plane, great circle, at this point. So, these are the 3 poles. Now, let us try to construct the projection of this particular plane in the crystal. What is the indices of this plane? This plane is joining 2 opposite edges. So, that means, and it contains the face diagonal. So, therefore, the indices of this plane is 0, 1, 1. We extend this plane. So, this is the plane, then we construct the normal to this and extend it to intersect the reference sphere. It intersects this here, and also it intersects, this is, it is halfway between this pole and this pole on this great circle. This is 0, 1, 1. Now, project it, we look at it from this particular point just opposite, diametrically opposite to 0, 0, 1. To get a 0, 0, 1 standard projection, we must look at 0, 0, 1 from its diametrically opposite point and try to project it on this projection plane. And this is what is done over here. Then it projects at this particular point, which is halfway angular distance wise, halfway between this point and this point. Now, to draw this type of projection, we often use the angular relationships between different crystallographic planes. For example, one plane has an indices H 1, K 1, L 1, this is the Miller indices, and this is another plane has H 2, K 2, L 2. Now, geometrically it can be shown that angle between the two is given by this relationship. Cos phi can be determined if the indices of the plane are known. And it is also possible to show that in cubic crystal, where these axes they are orthogonal. So, any crystal system where the axes are orthogonal, if a plane is like this, if a plane is like this and its indices is H K L, and normal to this plane is drawn here. Normal to this plane is UVW, and the angle between this plane HKL and its normal UVW is 90 degree. So, therefore, in place of H2K2L2, if you substitute UVW, you get this relationship if HU plus KV plus LW equal to 0. So, this relationship will be valid. For example, the plane 1 1 1 in a cubic crystal and the pole or perpendicular direction which is represented that also by 1 1 1, angle between these two will be 90 degree. And this relationship is very frequently used to construct a standard projection. Let us try to construct the standard projection of a cubic crystal on the projection plane 0 0 1. Now, obviously, projection plane is 0 0 1. So, center of this is 0 0 1 and this is the pole 0 0 1 and this is the plane 0 0 1 and the pole 1 0 0 1 1 0 0 will be located here and the pole 0 1 0 will be located here. And it is best illustrated by, let us try to do this exercise on paper. Now, here this is pole 0 0 1 which is represented by this point. This is 1 0 0 which is represented by this point. This is 0 1 0 is represented by this point. Now, the opposite of this, the point diametrically opposite of this is this. So, indices of this will be minus 1 0 0, we call it bar 1 0 0. Like this, it will be 0 bar 1 0. And we have shown little while ago on the reference sphere how to locate the pole 0 1 1. So, 0 1 1 will be located between these two poles on this equator. This is 0 1 1. Now, here if we recollect the relationship between two planes of indices h 1 k 1 L 1 and h 2 k 2 L 2, we try and find out the angle between 0 1 1 and angle 0 0 1. So, this is equal to, is given by cos phi equal to the product of 0 times 0. So, this is 0 product this times this, that is 0, plus this times this, that is 1, and then it is root over h 1 square plus k 1 square plus L 1 square. So, which is root 2, and in this case particularly it is root 1. So, therefore, this equal to 1 over root 2. So, that means phi is 45. So, likewise, it is possible to index all this. This is also the angle 45 and its indices is 1 1 0, opposite of this is 1 bar 0. This point is 1 bar 0 0. Now, it is quite simple if we recollect this zone relationship, that is H u k v plus L w equal to 0. In that case, it is possible to show that if you add this and this, you get 1 1 0. So, that also will lie, that indices will lie on this particular plane. It may not give you the exact where, but somewhere in between these two, and then we can find out the angle between this and this, which also can be shown in the same way to be 45. So, this is here like this. Similarly, what is the index of this? This is 1 1 bar 0, which is, I think this is 1 bar, there is a mistake here, 1 bar 1 0. So, it is the diametrically opposite to this. This is 1 bar 1 0, this is 1 1 bar 0. Now, what is the index of this? How do we find out? Now, here if we add this and this, what do we get? We get 1 bar 1 1. So, that means 1 bar 1 1 lies on this great circle. Similarly, if we add this and this, we again get 1 bar 1 1. So, that means this lies on this great circle. So, therefore, the point of intersection is 1 bar 1 1. In the same way, you can show that this also you get by adding this and this, you get 1 1 1. Similarly, adding this and this also you get 1 1 1. So, index of this is 1 1 1. And then what is this? This is 1 bar 1 bar 1. This is 0 1 bar 1. This is 1 1 bar 1. So, we have indexed all this. So, now it is also possible to index the other directions as well. Say for example, you take somewhere in between the two. In between the two, you will get a pole. So, if we add this and this, you get 2 1 0. 2 1 0 will be halfway somewhere between the two. You can find out the angle using this type of that angular relationship, that cos phi. So, it will obtain some particular angle with this, another angle with this. Similarly, opposite of that will be 2 bar 1 bar 0. You join these and this. So, basically you join this line, you get this, and then you try and find out what is the indices of this. So, this is how it is possible to construct a standard 0 0 1 projection. Now, if you want to convert it to any other projection, like let us say we want 0 1 1 projection, then how will you do it? You can, this can be done by rotating this projections, and rotation of this projection is possible with the help of Wolf net, and I will leave it to you as an exercise. Now, often you may have to represent Miller indices of a pole in a cubic crystal or a standard projection. Say suppose this is a standard projection, how do you locate a particular pole which subtends a set of specific angles? Say suppose we consider this plane here. This plane has an indices h k l. The normal to this plane is this. Now, we want to represent this pole over here. Now, look at or measure the angle. This angle is rho, this angle is sigma, this angle is tau. And now, particularly look at this angle tau. This direction HKL that pole HKL subtends angle tau with respect to this axis C. So, that is this axis C is 0, 0, 1. 0, 0, 1 is located here. So, along the great circle or along the equator here, you can measure this angle tau, locate this point. And then you locate this angle sigma along this great circle and rho along this great circle, and this can be done vice versa. So, suppose here is a pole, you can find out these three angle and you can convert it, take cos rho and make it that cos rho, cos sigma, cos tau will be in proportion to HKL. So, basically if you can, magnitude of cos of an angle is a fraction. So, if you can with a suitable multiplier make it integer, then HKL will be the indices of the plane. So, with this we finish this chapter on atomic bond and crystal structure. Some of this exercise that I have given, it will be worthwhile for you to pursue that. I think the concept of stereographic projection is little abstract and you have to go through some exercise. Say suppose over here we try to find out, say we had just drawn a standard 0, 0, 1 projection which was shown here. Now, using this, say suppose we said that this is 0, 0, 1, this is 1, 0, 0, this is 0, 1, 0, this is 1, 1, 0, this is 1 bar 0, this is 0 1 bar 0, this is 0 0 1 bar, and this is 0 1 1 bar. So, this is 1 1 bar 0, this is bar 1 0, this is 1 1 bar 1, this is 1 1 1. Now, let us try to find out, say suppose the plane 1 1 1, say which of these directions, say try to find out the directions type of 1 1 0 directions which lie on plane 1 1 1. Now, here this is the pole of 1 1 1. On this try and construct the plane 1 1 1. Plane 1 1 1 will be represented by a great circle and that will be at 90 degree from this. So, along this diameter using Wolf net, try to locate a point which is 90 degree and try to construct a great circle which passes through this point. And then you try and find out what is the indices of this. Same thing can be done with respect to this 1 bar 1 bar 1 pole. So, corresponding to that there will be a plane like this. What is the indices of this? Say construct a plane try to find out indices of each of these points of intersections. So, with this we end this topic on atomic bond and crystal structure, and from time to time we will be in subsequent lectures will be referring to these parts in detail, and if you go through this example, this will help you to understand subsequent lectures. To sum up, we covered that atomic structures, how the atomic structures and atomic bond affect the properties of engineering materials. So, what is the difference between metallic bond and covalent bond? Why metallic bond exhibit good conductivity? Now, in metals, what type of crystals are there? There are 3 types of crystals primarily: face centered cubic, body centered cubic, and hexagonal close packed. We looked at some of the characteristics of these crystal structures. We learned how to represent different planes and directions in a crystal using concept of Miller indices. Miller indices in case of hexagonal close packed structure has little problem. If we follow the conventional Miller indices, we often do not come across similar indices for similar types of plane. So, therefore, here we had to introduce the concept of Miller-Bravais indices using 4 indices, but you do not need 4 indices to represent a 3-dimensional structures. So, one of these is redundant. So, it follows a definite relationship with the other 2, and then we looked at standard projections. We looked at 0, 0, 1 standard projections, but it will be worthwhile to construct few other standard projections using Wolf-Net or using the angular relationship which I had given you. And if you try and do find out what will be the standard projection, how will the standard projection 0, 1, 1 look like, or a standard projection 1, 1, 1 look like. And this standard projections, looking at the standard projection, it is also possible to determine the symmetry elements. So, maybe if you look back, you will find out, say in this particular case, say this particular cube axis, if you rotate, you have one point here, one point here. So, that means, if you give a 90-degree rotation, it comes to occupy similar positions. So, this axis is actually a 4-fold symmetry. Similarly, try to find out what type of symmetry element is represented by 1, 1, 0. Similarly, what type of symmetry elements is represented by 1, 1, 1, and try to be convinced using standard projections that this exhibits 1, 1, 1 exhibits a 3-fold symmetry, whereas this exhibits a 2-fold symmetry. With this, we end this chapter, and we will next chapter we will look at some of the tools and techniques which we use in principles in physical metallurgy to find out structure property correlations. Thank you.